Today we are going to learn. Today we are going to learn how we can model a cantilever beam in a finite element software. So before going to that, let us see what is cantilever beam. The cantilever beam is a beam where one end is fixed, and other end is free. Okay, that is basically your cantilever beam. So here we have this cantilever beam where we have fixed this beam using some screw, and then we use some heavy load to have proper fixity on the fixed end. And other end we apply the load. So here the load is 10 Newton load that is acting at the free end. Now if you see the beam, you see the geometry of the beam. So this is the thickness, that is your 10 mm, and this is your width, that is your 50 mm. These things are given there, and property is given there as your Young modulus is 30 GPa and Poisson ratio is 0.3. Density is given there, but since we are doing static analysis, density will not be necessary for our analysis. Now, thing is that we can model a cantilever beam in three ways. One is your three-dimensional body. If you want to see how the stress is changing throughout the body, in that case, we can model the beam as a three-dimensional body. If you are only interested to see how much deflection is coming and what the direction is coming at the end, in that case, you can use this 1D bar. Another way, if you want to see how a plane, how the mid plane is waving, how the deflection pattern is coming, and how the mid plane is waving, in that case, we can use the 2D model. Now we can model. Now we have learned we can model a beam as a three-dimensional beam, as a 2D beam, as a 1D beam. So here we are going to model this beam using 1D element, in 1D element in ABAQUS. Okay, so 1D element here, ABAQUS use as a B31. B31 is your linear element, and then we have B32 element, that is your quadratic element. Okay, so we will model the beam using 1D element. Initially use B31 element, and then we'll use B32 element. Okay, now once we model it, what is our objective? Our objective is to first find what the maximum deflection is coming, that is note down, and then we'll try to go for convergence study. We'll see if we increase the number of elements. If we increase the number of elements, okay, then how our result is changing. You will observe that after certain number of elements, our result is not changing. So then we can say that is a converged result. If you use B3 element, if you use B31 element, if you use B31 element, you will observe after certain number of elements, we are getting convergent result. Again, if you use B32 element, you will observe after certain number of elements, you are getting convergent result. So convergence is the one thing where we are not able to improving the result much. Okay, or other way you can say, if you want to improve the result much, in that case the cost, the time you are providing, that will be too much in comparison to the gain. In some cases you will observe that after 4 or 5 digits you are getting good result, you are getting similar result, but after 5 digits, after 5 decimal point, your result is varying. So if you again increase the meshing, you may get some good accuracy, but the time it will take, that will be enormous. So it's basically up to us, up to which digit we want to have our acceptable result. So here that is convergence is coming. So here we will observe that after certain number of elements we are getting acceptable results. So we should be happy with that, because that result is matching with our experimental data. Okay, so that is our convergence study. So we will try to observe maximum deflection, then we will try to go for convergence, and then we will try to plot load versus displacement, how our displacement is coming with respect to load. Okay, we will see how it is occurring, and at the end we will try to match our result analytical model. So you will observe that our analytical model used to give deflection as your PLQ by 3EI. Okay, if you calculate it, you'll observe that I is equal to B dq by 12, I is equal to B dq by 12. Okay, if you put that value I, and then if you calculate the deflection, you will get deflection as 26.66 mm deflection is coming at this end. Okay, at this end. So now we will see that how we can model the beam using wire element and how much deflection we are getting, how we are getting the convergence result, whether our convergence result is matching with our analytical model or not. And once we agree with that, we can go for plot of our data, load versus displacement data. So we'll go for ABAQUS modeling using B1 element and then B32 element. Okay. One more thing you have to keep in your mind that ABAQUS do not have any inbuilt unit systems. So while defining the geometry and while defining the load, you should be very consistent with your unit system. Whenever you are defining the load and the geometry, should follow SI unit system or SI unit in mm. Okay, where you are defining the geometry in millimeter. Okay, so best way is to follow Newton meter unit. If you observe to know that if you follow SI unit system, then you are getting the value in some decimal places. In that case, you can use Newton meter unit. Okay, in that case, you can use Newton. Sorry, in that case, you can use Newton millimeter unit. Okay, so you should try to prefer this unit systems. If you prefer this unit system, then there is no need to modify anything. You can provide the length in meter, provide the force in Newton, you can provide the density in kg per meter cube. Now, if you want to provide the unit in SI MM system, in that case, you have to provide all the geometry in mm, you have to define all the force in Newton. Again, you also have to define the density in ton per meter cube. Okay. Now, if we define the input data like this, okay. Now, if you want to see output, if you want to see output as a stress, in that case, you'll observe that this value is coming as a MPa, Newton per meter square. If you define this unit system, then your stress output will come as Newton per meter square. And here, if you use SI unit system, in that case, our output, that is a stress, that will come as Newton meter square. So this way, you have to correlate your input data and output data. Okay, so you should always be consistent with the unit system. We should not mix one unit system with other unit system. Okay, in that case, you will get erroneous result. Okay, if you mix these unit systems, if you mix this unit system with this unit systems, okay, then you will get erroneous result. Okay, so ABAQUS do not have any inbuilt unit system. You should be very consistent while defining the unit. Now we'll go for ABAQUS modeling using 1D bar. Now here we'll see how we can make the cantilever beam in ABAQUS using 1D element. Okay, so here we'll click on part, and now here we'll choose 3D deformable, and then we'll choose where type. Okay, where, and then here we'll choose 5 as our working window size. 5. We've chosen is 5 because our maximum size of the cantilever beam is 1 meter. So 5 is our justified size. Now here we'll select this one, create line. Now we'll choose our first coordinate 0, 0, and we'll choose the second coordinate 1, 0. Since our length of the beam is 1 meter, so now you have created 1 meter length. Now I will press escape button and then I will press done. We can see we have created a beam of having dimension 1 meter. Now what we will do, we have to apply material property. So here we can create material library. Okay, here you can create material library. Here we can provide from mechanical to elasticity. Now from elasticity, here you can choose elastic, and we'll provide 30 GPa, and your force ratio is 0.3. This way we can create material. Here you can see how many material you have. Since we have created only one material, we can create a library of material and we can save it. Okay, and later on you can assign the material in the section part. Okay, now here we can create a section. Since we are using beam, so here we'll choose this beam. Okay, and here type also will be in beam. Now here you just see it is section name. Here you have to create that beam profile. So how the beam profile look like, since we have a rectangular cross section. So you will choose rectangle and you click in continue. Now here the dimension of the cross section is 50 mm, so 50 to the power minus 3, and then 10 mm, 10 to the power minus 3. Okay, now here you just see I am keeping all the dimension, all the geometric dimension in meter, and I will provide the load in Newton. So whatever the output I will get, all will be in Newton meter. Okay, here you have to keep one thing in your mind, that Abacus do not have any inbuilt unit system. So you should be very consistent with your unit. Either you can use Newton meter or you can use Newton mm. Now, if you use any other unit system, that time also you should be very consistent with the unit system. Otherwise, you may not be able to correlate your result. So here my suggestion is that you always should be consistent with your unit system. So now we have created the profile. Now here you can see we have selected the material one, that already have created in the material. So in the section we can create profile, and we also can choose whatever material we want to provide in that section. Now here you can click OK. So similar to our material library, here also you can create a library for the section. Now here you have to assign the section to the beam. So I have selected this third option. Now it is saying, here you can see it is saying select the region to be assigned section. So here I have selected. Now I am clicking on the done button. Now here you can see we are assigning the section 1 that I have already created. Here it is type is beam, and material 1 we are assigning it, that material 1 also I have already created. So now we'll click OK. Now here you can see that this color has changed. Now color is changed to green. So here you can see that since the color has changed, you can be sure that you have provided the material property. Now what we are going to do, we are going to go to the assembly. In the assembly, what we used to do in the assembly, we used to create instances, and thereafter we used to work on the instances. Here we can create lot of instances, but for this analysis one instance is enough. So here you can click, and here you can see we can create instance by two types. One is dependent and another is independent. So if you choose dependent instance, then you have to mesh it in part. If you use independent instance, then you can mesh it in instance. Okay, so by default it is coming dependent, so I am choosing it as a dependent instance. Now what we are going to do, we are going to go for steps. So here in the steps we can define what type of analysis we want to perform, whether it is static analysis or it is dynamic analysis or it is buckling analysis. So whatever analysis you want to perform, you can define it in the step. So since we are going for static analysis, here we'll click on the steps and then we'll go for general static, and we'll continue. And here you can see there is some options to modify. Okay, but we'll go for default value because this is simple analysis, so we'll go for default value here. And here we have two other options. One is the field output. We can ask about, you can ask Abacus to give some field output. So here you can see in the field output we have lot of options: stress, strain, displacement, force, all the things we have. Okay, you can ask Abacus to give some specific output which is required for an analysis. Or in the field output, in the history output also you have various options. Okay, you can ask Abacus to give this request. We will see how we can provide it. We will see while doing the convergence study, while plotting the load versus deflection graph. We will see how we can ask Abacus to provide some specific data for us. Now we have defined a step. In the step, you can check. We have defined a step. We have defined a step as a static general since we want to perform a static analysis. Now we will go for meshing. Here we can do the meshing by two ways. One is that by choosing size of that element, global size of the element, or by numbering systems. Okay, we'll see how we can do that. Now here we'll click it here, and here you can see it is saying that dependent part instance. So mesh cannot be done in the dependent part instance. So what we can do, we can click this part here, and here we can click again. Here you can see it is asking that what is the global size. Since we have 1 meter beam, so what we can do, we can put is 0.5 so that it will create only 2 elements, and later on we will increase the number of elements and we will see how we can do the convergence study. Okay, how we can do the convergence study, that we will see. So now we have created 2 nodes. So here in the seed we used to create node, and once you click on the mesh and define and click on yes, here we used to connect the nodes and we create the element. Okay, here we used to connect the nodes and we create the element. So ABAQUS by default is to create linear element. Okay, by default it is to create linear element. If you want to change higher order element, then you can go to this mesh and you can go to the element type, and then you can select it and click on done. Here you can choose higher order element. So here you can see by default it is linear element. Here we have quadratic type element that you can choose, but here first we'll go with linear element, and then we'll increase the number of element. We'll see how we can get converged result, and we also see how our quadratic element is affecting our result. So here we have chosen 2 element and type of element is linear element. Okay, now what we are going to do, we are going to apply the loading. So in the loading part, you just see there is 2 things. One is that loading, create load option is there, and another is boundary condition. So first we will try to apply the loading, and then we will apply the boundary conditions. So to apply the loading, here we will choose this option, and since we have cantilever beam and with a point load, what we are going to do, we are going to select concentrated force, and we'll choose this node and we'll apply our concentrated force. So our force basically will be in the negative y direction. So here we'll put -10, and -10 here we just see we are putting here in the CF2. We are forwarding in the CF2 and we are releasing, and here you can see that CF1 is corresponding to your force along x direction, CF3 is force along z direction. Since we want to provide along y direction, so here we are providing CF2 is equal to -10. Minus means it is negative sign. So here you can see we have provided the load in the negative direction here. Okay. Now we'll apply the boundary condition. So apply the boundary condition, we can choose Lancaster options or displacement type boundary condition. Okay. So here you just go with Lancaster option. So here you just choose the boundary, choose the node in which you want to apply the boundary, and then click on done. And then here you just choose Lancaster option. Lancaster option, here you can see all the displacement content along the degree of freedom are 0. U1, U2, U3, UR1, UR2, UR3 all are 0. U1, U2, U3 is the displacement along X, Y, Z, and UR1, UR2, UR3 are the displacement on the rotation along X axis, along Y axis, and along Z axis. So we are providing all displacement are 0. That means we have fixed type of boundary conditions. Those are in the beginning stage. They can choose Lancaster options if your boundary condition is fixed. Okay. If you want to choose any other boundary conditions, then you can go for displacement type boundary conditions. Here also you can go, and here you can see you have U1, U2, U3. You have a choice that which degree of freedom you want to restrain and which degree of freedom you want to make free. Okay, so depending on your boundary conditions, you can choose this constraint. Okay, if you have simply separated boundary condition, in that case you have to choose some degree of freedom are free, some are restrained. Okay, so depending on your type of boundary, you can choose that constraint here. Since we have fixed boundary conditions and since we are in the beginning stage, we will choose encastle options to represent a fixed type boundary condition. Okay. Now here you just see we have created the part, we have created property, we have provided the property, and we have done the assembly. We also have done steps. In the step we have provided, we have chosen static generator to perform static analysis. Loading also we have provided, and meshing also we have done. Now we'll go for job, and then we will create the job. Okay, job 1 is your name. Here we'll continue and make it okay. Thereafter you can go here, okay, in the job manager, and you can submit it. So here it is saying that we have to provide beam orientation. It is saying that we have to provide beam orientation. So here beam orientation, here we have to provide in the property. If we use, I should mention it earlier, if you are using wire type element, in that case you have to provide orientation of that element. Okay, so in the material property you have to perform one more job, that is your beam orientation. So here we have to choose this one along with material property, along with section, along with your assigning section. You have to do this job assign of beam orientation. You have to click it here, and then you have to choose it, and here you just see it is saying that select the region to assign beam section orientation. So I have selected it. Now what I'll do, I'll click on done. Now here it is saying that enter an approximate normal direction in one direction. So here it is saying the tangent vector is shown. So this is your tangent vector. Automatically this will be your normal direction. So I will choose it as it is. I will make it okay. Then again I will click on OK. Now here we have assigned the beam orientation. Okay. Now what we will do, we will go for job and we'll submit the job. Now the job is completed. What we will do, we'll go to the result, and here we'll see what is the maximum displacement is coming along the U2 direction. Okay, here you can see our maximum displacement is coming 2.628 e to the power minus 2 meter. That means 26.28 meter. Okay, so here we have used two elements and we are getting this displacement. We are using two elements, we are getting this displacement. Now we will increase the number of elements. We'll increase the number of elements to 5 and then 10. We'll see how our result is converging. Okay, we have used two elements and now we'll use 5 elements. So how to do that? We'll go to mesh again, and then here we'll choose this option, seed by edge. Here we have to choose part. Here we'll go for seed by edge, and we'll select the body and we'll click on done. Now here we can choose by number. So here we can choose 5 number of elements. Okay, so here it is saying that if you do this operation, your old mesh will be deleted. Okay, fine. It is not an issue for us. So let it delete, and we'll create the seed number here. Okay, and then we'll click done, and now we'll assign the element here. Okay, we'll do the meshing. That means basically we are assigning the element. Now again we'll go to the job, and again we'll submit it. Now here job is completed. We'll go to the result. We'll go for U and then your U2. Here you can see our displacement for 5 element is 2.661 e to the power minus 2 meter. Okay, now here you can see with 5 number of element we can get converged result. Now what we can do one more trial. We can go to the mesh. Now again we can increase the number of element from 5 element to now we'll increase to 10 element, and what we'll do, we'll assign the mesh, and now we'll go to the job, and again we'll submit. So now with 10 element, we will see how much result is coming. Now once we get the result, what we can do, we can plot it, to see how the result is converging. Now job is completed. Now here we'll go to our U and U2. Here also you can see it is coming 2.665 into the power minus 2. Okay. Now one more thing we'll do. Now we'll change our type of element to our higher order element. So how to do that? We'll go to the mesh, and in mesh, if you go here, toolbar mesh, here we can see type of element type. Now you can choose the body, and here you can choose your quadratic element. Here you can see it is your B32 element. Quadratic element means your B32 element. Okay. Now we have assigned the mesh. Now again we will now here we'll submit the job, and we'll see how much result is coming. So now here what we have done, we used 10 number of element and we have used B32 element. Now we'll see what is the result is coming. Initially we have used B31, that is your linear element. B31 we have used. Now we have used B32 element with the 10 number of element. Now we'll see what is the result is coming. So now here we'll click the result and we'll see U2 is coming. So U2 is 2.667. So now here you can see now result is not changing much. It is almost to our exact solution. So if you want to find the exact solution, you can find our exact solution as your PLQ by 3EI. And if you do this, okay, if you find that I is equal to BDQ by 12, okay, if you choose I is equal to BDQ by 12, and if you know the P, if you know the length, and if you know the E, then you can calculate P LQ by 3I. That time we'll observe our displacement is coming 26.66 mm. Okay, here also we are getting 26.667 mm. So you can see we are getting very close result with our analytical model. Okay, so this is the way we have to do convergence study. Okay, now we'll try to see how we can plot our load versus deflection graph. How we can plot our load versus deflection graph. Now here we will try to improve. Now here we will increase the number of element from 10 to 20, and we'll see we will increase the number of element from 10 to 20 and see what is the deflection is coming. What is the deflection is coming. So here we'll go for meshing, and then we'll run it one more time, and we'll see what is the deflection is coming. Now we'll go to the result. We'll go to U2. So your deflection is coming 2.667. So here we'll write 20 element and deflection is 2.667. So here you can see still there's some scope. We'll see how. Now again we'll try to increase the number of element to 40. Again try to increase the number of element to 40. So here increase the number of element to 40, and we'll do the analysis again. We'll see how much deflection is coming. Here you can see the deflection is coming 2.667. So now 40 element, here deflection is 2.667. Okay, now you can see now result is not improving much. So with 40 number element, or you can say with 20 number element, we can have good result. With 20 number of element with your quadratic element, we can have good result. With 20 number of element with quadratic element B32 element, we can have converged result. Okay, now what we are going to do now, we'll see how we can plot the load deflection graph. Okay, so just now we have learned how to do the convergence study. So here we have plotted it and we have learned how to do the convergence study. So here we have seen that with 20 number of element and with B32 element, we are getting a result which is acceptable to us, and further increasing the number of element, the result is not improving. Further increasing the number of element, the result is not improving. So we'll accept our 20 number of element for our further analysis using 1 dB element. Now we'll see how we can plot the load versus deflection graph. To do that, what we have to do, we have to get the data displacement for a particular node, and also we have to get the forces what we are applying here. So ABAQUS directly will not give the force value. ABAQUS normally give the value as a reaction force. So what we will do, we will select the support node and we will try to find the reaction force which is acting in the y direction, and we will try to find the deflection which is acting in the other node. Okay, now here we will, now to do that we have to create a node set. To do that we have to create a node set. So here we will go to the tool, you can go to the assemble, then you can go to the tool, then set and create it here. Now here you can create displacement node. Okay, the name node displacement for which we want to find the displacement, and we are continuing it, and we will select this node and we'll click on done, and one more node set will create, that is your support reaction. So here you can write RF2. Okay, and we'll choose this node and we'll choose this node. So now we have created node set. Now here what you have to go, now here what you have to do, you have to go to the step, you have to go to the step, and then here you have to go to history output, and here you can write your displacement. Okay, you can write displacement. You can continue. Here instead of whole model you will just set, you just select set, and here you just select this. This is one node, and for this we need the displacement along U2. Okay, so now we have requested for U2. One more request we have to do, we have to go for reaction. We have to go for reaction. So now just write reaction here, and here again you just select set, and then you just select RF2, and here you just select RF2. Okay. Now if you do this job and if you run the program one more time, if you run the program, ABAQUS will create displacement. ABAQUS will store the displacement in the node set of displacement node set, and ABAQUS also will the reaction corresponding to our node set. Okay, now what we have to do, we have to go to our result, and here we have to click on this button, that is your create XY data. So now here we can see this ODB history output. Since we have requested in the ODB history output, so here we have to go through it, and here you can see that we have U2. Okay, we have U2, one node we have selected, and we can save it as your displacement, or you can write end displacement. And one more thing we have to do, you have to select this one reaction force, and we can write support reaction, and we can save it as it is. Okay, now here you can see it is showing force with respect to time, and if you see the displacement, you can see the displacement also is showing with respect to time. Now here you can see displacement is showing in opposite order, minus again. Okay, it is going opposite order. Okay, now since force and deflection both are coming with respect to time, we have to operate on the XY data one more time. So here you can go to that operate on XY data, and then you can use combine here. Now you have to use minus sign here because displacement was coming in opposite order, and here you can select reaction. So what I did, I just use mouse and click twice, and here I can click on the plot button. Now you can see we can get our force versus displacement. Here you can see force versus displacement. Okay, so this is the way we can plot the force versus displacement graph. Now you can save this file. You can go to the file. You can save this image. You can go to the file and go to the print command, and then you just select it here as a grayscale and select as a file. Now here you can select as a TFF format, and you can give some name like this. Okay, now here you can see it has created the file at C and temp folder. Now you go to the C drive and temp folder, and here you just try to find G. Okay, now here you can see it has created force versus displacement file. Now you can copy this file and paste it in your project report, and you can submit it. You can paste it in your project report and you can note it down. You can copy it and paste it to make a report. Okay, so this is the way basically you have to model a 1D beam in ABAQUS. Okay, so what we have done, we have initially created part, and then we have defined property, then we have click on assembly, and then we define the steps, and then we define load. We also define meshing, and then we have submitted the job. So once we submitted the job, we get some result, and thereafter we have conducted a convergence study. Once we satisfied with the convergence study, once we decided that which element we should use and how many number of elements we have to use, once we decide that, then we have tried to plot the load versus displacement graph. Okay, and then we have saved it. This is the way basically you have to model a beam in ABAQUS. You have to model a beam in ABAQUS. So I hope you get some idea. Okay, thank you. To discuss about the boundary condition. So we know that for a fixed boundary conditions, we have our vertical displacement is equal to 0. We used to have horizontal displacement is equal to 0, and the theta rotation also used to be 0. Okay. Now, if we use three-dimensional body, then we'll have V along with have your displacement along the z direction. Okay. If you have three-dimensional body, in that case we have displacement along all the axes. For example, this is your x-axis, this is your y-axis, and this is your z-axis. So for a three-dimensional body, you have displacement along x, you have displacement along y, and you have a displacement along z. Now, along with the displacement, you also will have rotation about x-axis. Along with the displacement, we'll have rotation about x-axis. We'll have rotation about y-axis and rotation about z-axis. If you see the ABAQUS, we do denote the displacement as U1, that is your displacement along x, your displacement along y, your displacement along z. Okay, x, y, z, that will basically interpret as a 1, 2, 3. Now, if we see that your fixed boundary condition, so here in ABAQUS, you will see there is one option that is your encaster. Okay, the encaster option, if you choose that case, basically you are doing U is equal to 0, U1 is equal to 0, U2 is equal to 0, and u3 is equal to 0. Along with that, ur1 is equal to 0, ur2 is equal to 0, ur3 is equal to 0. Okay, so ur1 is equal to rotation about x-axis, ur2 that is rotation about y-axis, and ur3 that is your rotation about z-axis. Okay, these all are 0, so we ensure our fixed boundary condition. So if you are in the beginning stage in find L1 model in ABAQUS, then you use n cluster option if you want to represent fixed boundary condition. Okay, in that case you can use this n cluster option in ABAQUS to represent the fixed boundary condition. Okay, now here if you have a simply supported case, like this, then you have to think that which degree of freedom will be free and which degree of freedom there will be constant. Okay, so here again we will have a x-axis, y-axis, and z-axis. Okay. Now we know for fixed condition all will be 0, but for simply supported case only vertical will be 0. This here and u will be 0. Okay, vertical displacement, that is basically here you can say z will be 0. Displacement along x-axis will be 0 at this end. Here will be this vertical displacement will be 0. Okay, here we'll allow theta will not be 0. Here also theta will not be 0. Now we are talking about which theta, that also very important. And one more thing you have to keep in your mind, that how the load is applying. You see in the beam load is applying in vertical direction. Okay? Then if load is applying in vertical direction and there is no force along x-axis, Okay, there is no force along x-axis. In that case, we will observe that there is no horizontal displacement. In that time, you may choose u is equal to 0 and you may not choose u is equal to 0. That will not going to affect your result. Okay, so here you have to ensure that there is no force acting horizontally. Okay, there is no force acting horizontally. In that case, this boundary condition you may not give. So now it's basically all depend upon how load is applying. Depending on that, you have to choose the boundary condition. How the boundary condition is going to behave after loading condition, that you have to judge, and depending on that, you have to apply the boundary condition. So if you are in the beginning stage, in that case, if you have a n cluster, if you have a fixed condition, in that case, you choose n cluster options, or you can go in displacement option. That boundary condition, there is a displacement. There you can choose u1 is equal to 0 manually. You can choose all are 0. In that way also you can ensure your fixed boundary condition. If you have simplest ordered case, then you have to see in which coordinate axis, you have draw that figure, whether it is in your xy plane or it is in yz plane. Depending on that, you have to make the constant. Depending on you have to provide the constant, whether u is equal to 0 or whether y is equal to 0. It will depend how you make the geometry, whether it is xy plane or it is in this plane or it is in this plane. Depending on that, you have to provide the boundary conditions. Here we will see what are the boundary conditions you can provide. So the problem here we have cantilever beam. Okay, the problem you're solving is the cantilever beam. So one end will be free and we'll apply the load at that end, and other end will be fixed. Now to fix the conditions, we will see what are the boundary conditions we can have in ABAQUS. So here we have mechanical type boundary condition, that is basically dealing with your displacement or rotation. Okay, that is basically dealing with displacement, rotation, velocity, like that term. Now For most of the problem, for most of the simple problem, we can apply this type of boundary condition, right? That is your symmetric, antisymmetric, and n-cluster. Okay, so n-cluster is basically one loading condition where all the displacement value are 0. N-cluster is basically one loading condition where all displacement value are 0. So this value we can choose. Okay, if you are not sure which degree of freedom is free, which is fixed. Okay, if you are not sure about it, in that case, you can use the n-cluster conditions. Okay, so here what I did, I just select that edge line and then I give that condition n-cluster and make it okay. So here you can see I already have created boundary condition 1. Okay, now you have created boundary condition 2. Now what happened? ABAQUS will apply both the condition at the same point. Okay, but that is not required. So what we can do, we can basically cross this one. Okay, we can deselect it one. Deselect this one. So now you can see this previous boundary condition is there. Okay, so here we'll see what boundary condition we have applied here. Initially, we have made the boundary condition as your U3 is 0 and UR2 and UR3 also is 0. Okay, so that we have provided because for fixed boundary conditions, we know that for fixed boundary conditions, we know this vertical displacement will be 0. This case, this your U3 will be 0. And then we can have, we will have rotation theta is equal to 0. So theta, this rotation here will be 0. That we can ensure by considering rotation about this. Is basically rotation about this axis. Okay, basically you can consider theta is equal to 0. That is our u r2 is equal to 0. That we can consider. Okay, these two conditions. Okay, and third condition we used to have that u3 is equal to 0. Okay, v1 u1 and these conditions normally will satisfy for a cantilever case. Simply we can say that your vertical displacement is 0, horizontal displacement is 0, and rotation also 0, which to satisfy for two-dimensional case, x and y cases. Okay. Now, if you are analyzing three-dimensional body, in that case, all v will be 0, all u will be 0, all theta will be 0. Here we are solving it where we are applying the load only one direction, that is our third direction, that is our z direction. Okay. And this is our x, and this is our z. So what we did, we basically make u3, that basically you can say the displacement in the z direction is equal to 0. Okay. Or we can say vertical displacement is 0, in that way you can write. And theta z, or here u r3 is 0. That is sufficient for this case. Since we are applying only vertical load, so automatically u displacement automatically will be 0. So since we are not applying any force horizontal direction, so this part we may not provide. But in case some force act in this direction, in the x direction, okay, in that case you have to ensure this is 0, otherwise it will show some rigid rotating motion. Okay, so this is the things we have here. You can see what we did. We basically we did u3 0, and you can remove this part also, and you can check how much value we are getting it here. Let us see. The board is saying too many attempt or errors elaborate something. Okay. Here we can check the boundary conditions because only boundary condition we have changed. Then why it is saying you are two rotation about. Oh, what why exercise? Yeah, you are two. Yeah, it's you are two. Here we'll discuss about the boundary conditions. So see, we have the cantilever beam. We have the cantilever beam, and we're using it using a cell element. And what we did, as per notation of ABAQUS, what we did, this is basically we have made in this X and Y plane, and in this direction, okay, in this direction we have that loading. From the top, we have the loading. From the top, we have the loading. Okay. Now, the cantilever beam, that means one end is fixed, other end is free. Okay. Now, fixed conditions you can ensure in ABAQUS by various way. One is that more common approach is that NK star. Okay, NK star. If you see NK star, ABAQUS basically define it that all the displacement quantity is zero. Whatever the displacement quantity you have, all are zero. U is equal to zero means all U1, U2, U3 is equal to zero. That is basically corresponding to displacement along X is equal to zero, displacement along Y is equal to zero, displacement along Z is equal to zero. Okay, and all rotation is zero. You are one, you are two, and you are three. All are zero. So you are one, you are two, you are three. Basically, rotation with respect to X axis is equal to zero. Rotation with respect to X axis is equal to zero. Rotation with respect to Y axis is zero. Rotation with respect to Z axis is zero. So basically, a node can have 6-degree freedom. A particular node can have 6-degree freedom. So here, if we consider the cell, we can have few number of nodes, 1, 2, 3, 4 nodes we have considered. So each node will have 6-degree freedom. 6-degree freedom in the sense U1, U2, U3. Okay, U1, U2, U3. That is corresponding to displacement along X, displacement along Y, displacement along Z, and we have three rotation. Here you are one, here you are two, here you are three. Okay, that is basically rotation with respect to x-axis, rotation with respect to y-axis, rotation with respect to z-axis. Now, if we use NK star conditions, what we are doing, we are saying that all the displacement component is 0. That is basically most common approach to define fixed boundary conditions. Okay. Now, if we think of your idealistic conditions, if you think of idealistic condition for this case, we have that beam and we are applying point load here. Okay, we are applying a point load here. We will see how we can ensure boundary condition which also represent fixed type of boundary condition. That is basically you can say alternate type boundary conditions. Okay, alternate type boundary conditions. So here you can see if we know that fixed condition means vertical displacement or V, that is here U2 is equal to 0, or you can say right displacement along y direction is 0 if we are considering this is your y and this is your x, okay, like that. And we have rotation is 0. Okay, so what we are doing, we are basically considering this node, and what we are defining your vertical displacement is 0, rotation about this axis 0 at this end. So basically there is no displacement here. So there is no rotation here. There is no rotation here. Basically, there's a displacement. Oh, sorry. Theta is 0. Theta is 0. That means there is no rotation here. Okay. That basically indicating the rotation about this y-axis is equal to 0. Theta is 0. That means theta y is equal to 0. Okay. But here it will be UR2 will be 0 for this case. Okay, because ABAQUS y-axis is basically indicating by 2 notation. R means rotation, U basically is common term which represents displacement. So basically displacement in terms of rotation with respect to y-axis. Okay, that also we can ensure. Another thing we used to define that your U displacement. Okay. Now thing is here that we have that cantilever beam and we are applying point load which is acting vertically. Okay, so there is no load, so there is no load along this direction. Okay, so obviously there will be no chance of having displacement this side. Okay, there are no chance of having displacement along this side. Automatically displacement will be 0. So you can make it 0. Okay, or you can leave it. Since we are applying load vertically, only these two conditions, V is equal to 0 and theta rotation is equal to 0. Okay, now here you can see theta is 0. That means theta with respect to which axis? That we have to see. That you can judge by seeing that your ABAQUS model. Okay, by seeing the ABAQUS model, here you can see model. Here you can see, so this is your x-axis, this is your x-axis, and y-axis basically like this. Okay, so here our rotation theta y will be 0. If you plot, if you make the geometry in the xz coordinate, in that case theta z should be 0. But here we made the geometry in the xy plane, so we'll have rotation theta y will be 0. Okay, and we'll have basically our vertical displacement is 0. That we'll see how we can do that. So what we can do, we can check at what condition we can give. So we have discussed 2 points. One is that we can choose Encaster option. We can choose Encaster options to define fixed condition. And another condition is that you can choose a particular degree freedom and we can quickly constrain it. We can apply the constant. We just making the displacement and rotation 0 on a particular degree freedom. Okay, so as a beginner, what you can do, if there is fixed conditions, you use these Encaster options. You get that your fixed boundary conditions. Okay, and if you are in advanced version, you can try this type of boundary conditions where your vertical displacement, and basically your U2 is equal to 0 and UR2 is equal to 0, like that things. Okay, this condition you can try. Okay. Here we'll try both the method. We'll try both the method Encaster options, and We'll try to make u2 is equal to 0 and ur2 is equal to 0. We'll see whether we're getting the same result or not. We'll try both the method and we'll see whether we're getting both the result or not. Now thing is that this is not generalized case. It's depend upon how you are making the geometry and which is your x-axis, which is your y-axis, okay, and how it is going to behave. Depending on that, you have to choose these conditions. Okay, so you can choose these conditions if you are in advanced version. You know how the geometry is going to behave, then only you can choose these conditions. Okay, if you are very beginner and there is a fixed condition, then use this N-cluster option. So here, what we will do, we will see whatever boundary conditions we can provide. Here you can see I have created two boundary conditions. Let me delete it. Okay, so first condition we will see. First condition here we have defined your u3 is 0, basically the vertical displacement is 0, and rotation about ur2 is equal to 0. Now here you can see I have not made u1 is 0. Okay, since I have not applied any force along u, so that condition is not required to satisfy. So let us see how we are getting the result. So we'll run this program and we'll see whether we're getting the same result or not. Let us do what? Completed. Now here you can see we are getting it displacement. We are getting the displacement. That value is coming 2.658. Okay, so that value you just note it down 2.658. Now what we'll do, we'll apply the second boundary condition. We'll apply the second boundary conditions. Let me create it here. Mechanical, so we'll apply N-cluster option, N-cluster. So it is saying select the region to apply the boundary conditions. I am selecting it here and I'm applying N-cluster option. Here you can see U1, U2, U3 and all the rotation are 0. Now here you can see I have applied the boundary condition twice. So what I will do, I will deselect first one and I just apply the second boundary condition, which is our N-cluster option. Now what we'll do, we'll run the program. Run the program. Here